All right, so what we want to do today in section 6 is we want to look at some graphs of some of the trig functions, and they're going to be comboed with other things that we would do, like radicals or square roots or who knows what, just all kinds of different things. And so when we do something outside of the sine x or any trig function, it kind of takes on some of those same characteristics. So when you graph these guys, you want to make sure that you're in radian mode, and make sure that you may or may not have to change your viewing window at all. It just kind of depends on the different types of graphs. But what I've got here is I've got sine x squared. So here it is. It looks kind of like this: sine x plus x squared. There it is right there. And you'll notice that it's the sine graph, believe it or not. But remember, sine can only go from -1 to 1. And that's as small and as large as it's going to be. So when we combine this together with x squared, now you're talking about numbers that continually grow and grow and grow. So what you end up with is a small variation, very small variation, of the sine curve, and it's going to be in the shape of x squared. And it's not perfect x squared, it's got some curvies on it, but it's very, very, very similar. Okay, and so what you're going to look at in this section is just different ways that you can combine different graphs. Here's another one: y equals sine x times x squared. Looks like this. All right, it's a little bit different now. It kind of wobbles back and forth, as you can see. This probably isn't the best viewing window for looking at this graph, but you can tell that this x squared, it makes an impact on what the graph is doing. This guy right here has a huge impact over what the sine of x would look like. Now, just for some points of reference, this goes from -2 pi to 2 pi, and from -10 to 10. So both of these graphs are the exact same. So if I look at the sine curve on a normal 2 pi to 2 pi, I'm looking at something that's just very small, and it looks, it's going to look something like this. So when you multiply by that x squared, it has just a huge impact on what's going on. What about the sine of x squared, like the whole thing now? So let's look at this guy. He's going to look like this. And again, this is on the same viewing window, so from -10 to 10. Now on this, think about when you square a number out. You will always have a positive number. So instead of our graph falling below the x-axis here, notice that it always stays above. It's always above, and our normal sine curve shouldn't do that. Our normal sine curve should go below the x-axis. Remember, the sine curve goes from +1 to -1, and it's not doing that here. It goes from +1 to -1 for the range, and it's not doing that. It's staying above the x-axis. So again, altering what we're doing to the sine curve changes the graph of the sine curve. And then the last one is what happens when we put that radical inside the sine curve. Or not the radical, the power. So we'd have sine of x squared. And this also is an interesting looking graph, where he gets a lot of space towards the origin, and the further you get from the origin, the more oscillating back and forth type of look you have. And so right here, lots of space, okay? But over here on the edges, lots of oscillation, and that's what happens when you start squaring these numbers inside. Think about if you square 1, you get 1. Or if you square 1/4, you get 1/16. But if you square a number that's really large, like say 5, now all of a sudden you are up to 25. And so the further you get from the origin, the more this oscillates back and forth. And these are just different ways that you can manipulate and look at and work with the sine or cosine or any of the trig functions when you combine them with another function. So when you're looking at all of these four graphs, one of the things that we want to try to look for is periodic graphs. Periodic, remember, means that they just start to repeat. So which one of these are periodic and look like they might start repeating values? Well, on our x squared one, I don't know. It looks like it's just a parabola and nothing exciting here. This one, depending on what's going on at the edges, could be periodic, but it looks like the values from its maximum that's not shown on the graph to its minimum, which is, doesn't look like it's the exact same. When you look down here at this guy, now this does look periodic because the same values get repeated every single time. The same values of y's get repeated. And so I would say that this guy right here, which is the sine x squared, I would say that this guy is periodic. But and then with this last guy, he is not periodic because when you look at these oscillations, they are different. They are not the same. And so when you look at that, that just would indicate to us that no, this isn't periodic. So only one of these four graphs is. Okay, so what we want to do on this guy, looking at the function of sine x squared, what we want to do is verify the period. And this is really an interesting thing to do because it gives us an opportunity to work algebraically with what we know to be true inside the sine of x squared. So basically what we're going to do is we're going to trust that the period is 2 pi. Now we've talked about this before and we've seen on our unit circle that the period is 2 pi, and what we're wanting to show is that is a true statement. So the fun thing about this is we can look at that. So we would take we would just look at, say, the sine of x, just the sine of x. We would say that's equal to the sine of 2 pi plus x. Because no matter where we go on our unit circle, we can add 2 pi to that thing and we'll wind up right back in the exact same spot. So we're going to use this information right here and count it as true. And so what we want to do is we want to look at this function f of and then 2 pi plus x. And this is really interesting. It also will take a little bit of time maybe to sink in for you to understand exactly what's going on here. But what we're going to do is everywhere we see x, we're going to put in the 2 pi plus x. Or 2x plus, 2 pi plus x. I didn't write that right. This should be 2 pi plus x. So same for this guy. He needs to also be 2 pi plus x. And then it's this whole thing squared. So when I'm working on this guy, what am I really looking at? Well, I'm really looking at the sine of not 2 pi plus x, but what it's equal to, which is just x squared, which is the same thing that we started with, which is equal to the f of x. How cool is that? Okay, here's another problem where we want to show something is periodic by proving it algebraically. And again, we want to stick with what we know about the sine of x, which is that if I have f of x equal to the sine of x, then this is like saying that, hey, we're also equal to x plus 2 pi. And we looked at this same property on the previous problem. So we're going to do the exact same things. There's nothing different that's going on here. But what we're going to do is now look at it being cubed. Hey, cubed is different, right? Well, make your substitution. So substitute in x plus 2 pi. And when we do this, we want to look at, do we get the same things? And sometimes you don't. Sometimes you don't get the same things. Sometimes you get something that's totally different. Well, what does this look like when I substitute that in? It turns into this guy right here. It turns into sine cubed of x plus 2 pi. Okay, so far so good, no problems. Well, what is this really? This really is sine of x plus 2 pi cubed, and it's really, the cube is really out here on the whole function, not just on just the little single sine part. It's like the actual entire thing being cubed. Well, don't forget, what does this guy equal? This guy right here, he is equal to just x. Remember, anywhere you go on the unit circle, if you add 2 pi to it, you're back to where you started. So basically, we're looking at this whole thing being cubed. And let me just, for emphasis, show this whole thing. So this whole thing being cubed. And hey, guess what? Isn't this where we started? Because with our shorthand notation, so we can keep track of where things are, we're going to say that this is sine cubed of x. And again, this is, what is this? This is what our f of x originally started out as. And so that's all it is. It's periodic. It can be divided by 2 pi. You can put into both equations here, like in here for this guy, I can put 0 to whatever. I can put any number in here, and what I get out will always be from -1 to 1. That's all I can get out at any point in time. So when you're looking at this, just keep all that stuff in mind. Don't forget what you already know about things. And we know that sine is going to go from -1 to 1, and we know that we can put any number in for that. And because of these things, we know that we've got a periodic function.